All right, in this video we're going to look at conservation of mechanical energy with springs. So we've seen that the spring force is a conservative force, just like gravity. Therefore, work done by that spring force, or negative work done by that spring force, is associated with a gain in potential energy of that system, that mass spring system in the case of masses on springs. So this is where our Ekugus comes from. So now the total mechanical energy is not just the kinetic plus the gravitational potential, but it also has to include the spring potential energy. Now when you're doing a problem with conservation of energy, always ask yourself, is there a spring present? If not, this goes away, you cross it off, and it's just kinetic and gravitational potential. Also ask yourself, is there any work done by any non-conservative external forces acting on the object? So this would be the work done by an applied force, the work done by friction, the work done by a drag force, even tension and normal. They're non-conservative forces. If any of these are doing work, you cannot use delta E is equal to 0 for the Ekugus. So be very particular when you read the problem to see that it is a situation where you only have conservative forces in play. Therefore, you can use conservation of mechanical energy, delta E equals 0. So let's apply this to a vertical spring. So a mass M is attached to an unstretched vertical spring with constant K and released. What is the vertical equilibrium point? And then what is the maximum stretch of the spring relative to the equilibrium point? So let's start by finding the equilibrium point. So unstretched length of spring, sorry. And then you let the mass hang till it comes to rest. So we're going to call this stretch the delta X equilibrium. And this is unstretched. So unstretched means no stored potential, no spring force, right? The spring force only engages when you stretch it away from equilibrium. So at equilibrium, and we've done this problem before, we know that the sum of the vertical forces is 0. So you have the spring force acting up. So if I draw in a quick free body diagram, force of spring is acting upward on the mass, force of gravity acting down, so Fs minus Fg equals 0. Well, the spring force is just K times delta X. Now remember, it's positive because the stretch is in this direction downward. So it's really negative X times negative Fs, which becomes a positive K delta X relative to my reference frame. So I have K delta X minus mg equals 0, or K delta X equals mg. Delta X, and this should be delta X at equilibrium, is mg over K. And that's, again, something we derived a couple videos ago. Now, what if we look at the maximum stretch of the spring if we were to allow this mass to fall? So in this situation, you have the unstretched mass, and then you allow that mass to fall. And so what's going to happen is, and you saw this in your lab, it's going to fall through equilibrium, and it's going to stretch to some maximum length. So here is, so I'll try to keep these reference points the same. So here is unstretched, here is equilibrium, and then here is max stretch. And we want to come up with an expression for the max stretch relative to my equilibrium point. So let's set a couple boundaries. This is my lowest point. So I'm going to set my lowest point as my vertical position of 0. So that's my UG equals 0 joule point. This is my 0 potential mark. And then I'm going to measure the initial height of this mass when it's unstretched, and I'm going to call that my delta Y naught. So my initial height above my lowest point, and so I'm going to be comparing my initial to my final positions in order to come up with this expression. Now, if we look at that, remember this is, so let me call this position 0. This is my initial point. This is, we'll call position 1 down here. This is position 0, I'll circle it. And this will be equilibrium in here. Now, I held this mass at its unstretched length and let it go and let it fall. And so what I want you to notice is, since this is unstretched, as the spring stretches to its, what I call delta x max, delta xm, it's going to fall and stretch vertically the same distance that the mass falls vertically. So whatever height I lose in my gravitational potential, I'm going to gain in terms of my stretch. These two numbers are going to be the same. What I also know is when I reach the lowest point, the mass is going to fall down, it's going to stretch to max, and then come back up. So at this lowest point, I know that the velocity is 0. Therefore, my kinetic energy, and this is at position 1, V1 is 0, so kinetic energy at 1 is 0. So relative to my potential being 0 here, I'm going to have all spring potential here, where I had basically all gravitational potential, because it began at rest and then I dropped it. So V initial is also 0 meters per second. Therefore, K initial is 0 joules. Okay, so let's use conservation of energy and the Ekugus. So let's look at position 0, my initial position. My total mechanical energy initial will be my gravitational potential initial plus my kinetic initial plus my spring initial. Now we said initially I have no velocity, so my K is 0. I also am not stretched, so I have no spring energy. So my total mechanical energy initial is just mg times my delta y naught, my initial height relative to my 0 point. Now let's look at position 1. And that's my max stretch. So at max stretch, my total mechanical energy is going to be my gravitational potential at 1 plus my kinetic at 1 plus my U spring at 1. You can write these in any order. I'm maybe not consistent with that. But when we look at position 1, we know that I'm at my lowest point, and I've set that as my 0 potential. So this is 0. I also know that I turn around, right? The spring stretches to its max and then comes back. So at that moment, the kinetic energy is 0. But it's got now all this stored spring energy. I'm going to call this 1/2 K delta x max squared based upon the stretch of the spring. So now, if we want to get an expression for delta x max in terms of the equilibrium point, let's set up conservation of mechanical energy, which tells me delta E equals 0. The change in mechanical energy from one position to another is 0. Or another way of writing that is the energy at the initial position, total mechanical energy, must equal the total mechanical energy at the max stretch. And so I have my initial mg delta y naught has to equal 1/2 K delta x max squared. Now notice, when you're using Ekugus, there's no mass in my spring potential energy. Therefore, the mass doesn't cancel anymore. So be careful about that. Okay, now, how can I relate these two values? Well, I know that delta x stretch is the same magnitude as my delta y. So now this is measured as positive from here. This is measured as positive in terms of my stretch. And so I'm going to replace this y naught with a positive delta x max. So in here, now I get this cancels with one of these. And if I solve this for delta x max, I'll multiply by 2, divide by k, multiply by 2, divide by k, and I will get that delta x max is 2 times mg over k. Okay, so how is this relative to my equilibrium point? Well, this is my equilibrium point, mg over k. That's going to be the stretch at equilibrium. So my max stretch is going to be 2 times that, or double. So when we have a vertical mass spring system, the max stretch, I'll write it out, will be 2 times the stretch of the spring at vertical equilibrium. So there's an example of finding vertical equilibrium again, and then applying conservation of mechanical energy with springs and potential gravitational energy to solve for an expression for the max stretch.